Okay. So today I'm going to talk about a partial differential equation called surface diffusion. It's a geometric evolution problem. So we're going to start by trying to understand what it is. We're going to talk about how to derive it, this is uniqueness, and if there's time, about stability of the solution. So I'm going to write the name of the PDE. If you can't understand my handwriting, please tell me. I will have a good handwriting. Okay. So the first part is, what is it? Okay. So I might write SD instead of surface diffusion. Is a geometric evolution problem defined as follows. Okay, so we let u be a function from u cross 0t. U is in Rn. 0t is just an interval in R. Of course, n is like more or equal to 1. To Rn plus 1. Okay, so U is a parametrization an evolving hypersurface. Okay. Parametrization of an evolving hypersurface. What does that mean? So just an example is just like, so consider, for example, a curve in R2, but t equal to 0, you have the curve, and then you just change the shape. At time t equal to 1, maybe it looks like this, and then at time t equal to 2, it will look like this. And in our case, we'll want it to evolve continuously. Okay, so now I think we're, and then, so the hypersurface, we call it gamma t. So the PDE is, I will define the terms now. U of xt is equal to minus the Laplace-Bertrand operator with respect to the surface of the mean curvature at each point ux. Okay. And then you also need an initial condition. So it's u of x0 is equal to some function u0 of x. And u0 of x, u0 goes from Rn to Rn plus 1. U0 parametrizes the gamma algorithm. So what do the terms in the equation mean? So v of u of xt is the normal velocity. That means it's equal to the time derivative of u times the normal at each point u of x. So we have a surface. So this is gamma t. At one point we have an outer normal, so n is the outer normal. So this point will be u of xt. This will be the outer normal at u of xt. And we just multiply the outer normal by the time derivative. Gamma of t is the Laplace-Bertrand operator. That's from the operator. And h of u of xt is the mean curvature. Mean curvature at u of xt. So it's just the average of like the curvatures. Well, I mean, if it's just a curve, it's just the curvature at this point, but you have a surface or higher dimensions, you just take the average over all the curvatures. Like you basically the integral over a ball at that point. You take all the curves that go to the ball, and the average is the mean curvature. That's what's called the mean curvature. So this PDE it can model many things, and one of the main things it models like the evolution of thin solid state films. So consider at the high temperatures. So consider like, for example, a film of silicon, you increase the temperature at like half a melting point or something like that, and it evolves roughly according to this PDE.
May I ask a question?
Yeah.
The mean curvature, I mean, the definition I know is the mean of the two.
You can prove those are equal. You can prove those are equal.
Okay.
Because and so you can prove that it's equal to take so if you have a surface, a two-dimensional surface, and you take all the curves that go through it, and you take the smallest curvature and the highest curvature, and you take the average, that's actually equal to the mean curvature. Like that's equal to the average of all the curvatures.
Yeah.
They're both the same. All right. So this PDE, like as we'll see soon, depending on the parameter, but H is generally second order operator. The Laplace version operator is second order operator. So the PDE generally is fourth order, which means that many of the classical tools for PDEs you can't use, like the comparison principle or the maximum principle, or all those tools that are often used, you can't use for this equation. Okay. So we'll talk about three different things: derivation, well-posedness, and stability. So we'll start with derivation. So this PDE is the gradient flow. What does it mean? Is according to some norm, we're trying to continuously minimize some functional in the most efficient way possible. So what's the gradient flow? Given the functional f from x to r, this is Hilbert space. Hilbert space. The gradient flow is the gradient flow is the following equation. So you take the first variation of I'll explain what this means now. The first variation of the function f, the negative of the first variation of the function f, and you set it equal to the inner product. And this is in the direction of some psi. Okay, this is the inner product with respect to x. The first variation is just the directional derivative of x in the direction of psi. It's just literally the same definition as in like one-dimensional, like it's in calculus. Just instead of a function, you have a function. Okay. So an example I will use, like an easy example is if you take a function from Rn to R. So and you look at the definition. So the inner product would just be the inner product. This would just be equal to the gradient of f. Oh, so I made a mistake here. X. Okay, I'll just be more precise. X is in say H1 of R X. So X is like H1, this will be time. So you take the time derivative. So the first variable, X, for example, you can think of it as a function of time, but at each point in time, it goes to the Hilbert space X. And take the derivative in time. So the gradient flow is equal to, so you just look at the definition, and you look at function f in x, and just x of t as a point in, like, you just think of x as x of t, but just, it's just a point in time, you know, it's just like a point that evolves, like, that can evolve in Rn. Then those two are the same definitions, which is the gradient flow, like most of you are probably familiar with. Like, like the ODE that most of you are familiar with, and this is just a generalization of that definition. So we're now going to define like we're going to define like a particular Hilbert space, which will help us define surface diffusion of the gradient flow. So I'll just give some review. And I already wrote it once, but I'll just review it. H1 of say U in Rn is just U in L2 of U, such that the first derivatives are in L2. Oh, so that's H1 of U. I'm going to define H minus 1 of U. This is the Hilbert space we're interested in. So its element is U in the dual of this space, H1, such that this is equal to 0. When you integrate over U without over this U, then you get 0. And I'm just going to be more precise. I will just give them different names. Okay. So now what we want to do is we want to define the inner product for this space. This is the first thing we need to do. So, sorry? You want me to define the whole space? Yeah, so you got a vector space, V. Okay, so V a vector space. And it can be infinite dimensional. It can be like Banach space or Hilbert space. And the dual is just linear operators from T of V to R. The space of linear operators, T is a linear operator. And when you do this, you're just applying the linear operator. So, I mean, it's a little bit, just by looking at this, it's a little bit difficult to understand how those are like elements in the dual, but you can think of as elements in the dual as linear operators. Maybe you can look at linear operators and so T of U will be equal to a linear operator like this. Okay. So just an integral over V, and you just multiply by U. And you think of the elements in the dual as the kernels or the coefficients of the linear operator. You can think of it like that. And then this just means doing this. Well, this will be with 1 instead of U. All right, so let's see. Yeah. So we need to define. Okay. So now we're trying to define. We define the product. Okay. So this is one way of doing it. So we consider the following PDE problem, which is Laplace of U. So yeah. So this is either the Laplacian or the Laplace. If U is something like some hypersurface, the Laplace virtual operator with respect to U. Equal to f of x, and the average over U of U is equal to 0. So just consider this PDE problem. F of x is in H minus 1. Okay. So if f of x is H minus 1 of U, and you satisfy this property, we can show that this PDE problem has a unique solution. Right? So this is like if you take like a grad course in PDEs, maybe you've seen this. And then by showing that this PDE is a unique solution, you can show that this operator here, the Laplace of U, is invertible. So it has a unique solution. Solution U in H1 of U. Therefore, Therefore, Laplace U is invertible from H1 union U such U in H1. There's no connotation, that's fine. Is equal to 0 to H minus 1 of U is invertible. Okay. Of course, we know the inverse. And know the inverse. Laplace minus 1. Okay, this is just the notation for the inverse. And that you can see. Okay. So this is the inverse. So now we're almost done with the definition. The definition of the H minus 1 inner product is minus 1 of U. Inner product is let's call it this. Okay, this is the definition. There's many motivations for this, but we can define it like this. And you can check its inner product as well in all the properties. So now we're ready to derive surface diffusion. So consider the area functional A. A of let's say gamma equal to gamma 1. So just to take the area of gamma in a hypersurface. Surface gamma and let's say I rent this one. Okay. So this is just the area. So that you just take the area, and then you just apply the definition of a gradient flow. So what is it? It's minus. So those are just functions defined over this area. So minus the perversion of the area of U in the direction of psi is equal to the inner product U times psi with the minus 1 inner product. All right, there's the definition. We give it the initial condition, U of 0 equal to U0. And that you can prove, we can show, I'm not going to do it now, but we can show it is equal to surface diffusion. So surface diffusion, what it's doing is, and then gamma, this is the initial configuration. Configuration of the hypersurface. Right, so what is surface diffusion doing? It's continuously minimizing the area of a hypersurface in the most efficient way possible, according to the norm induced by the H-1 product. So some properties you will have, if gamma is finite, like it's bounded, or it's compact, the area will be decreasing, which makes sense, otherwise weird. But the difference between H-1 and other like spaces, the volume will actually remain constant. So when you look for the states and things like that, is related to like isoperimetric inequality and things like that. All right. So now we've derived, we have a derivation of surface diffusion. So we'll go to the second step of this talk, and we will talk about well-posedness. So what well-posedness classically, it basically means given initial condition. So in this case, we're looking at problem without boundary. So given initial condition, does there exist a unique solution to the PDE? And does the solution continue to depend on the initial conditions? So, well, so we look to go roughly we seek to find a class of initial conditions for which there exists a unique solution to the PDE to surface diffusion in some specified spaces. So the spaces where you will live are kind of important. So we will consider like the kind of a simple example just to understand it, because there's many ways of parameterizing the hypersurfaces. And let's try to consider the simplest parameter. So when we study the surface diffusion, we want to consider like a particular parameterization of the hypersurface. So to study this, in this talk, we will look into parameterizations. Parameterizations of gamma E as the graph of a function. All right. So let's draw that. My lines are not very straight. So this is R. This is the function U. So this is the function f of x from R to R. And each point here will be x f of t. Sorry, so f of R to R. It's f from 0 to R. Notice in this page, you don't want to have boundaries of all R over R. So actually, the concept of area and volume don't make that much sense, but it's a good example to start with. Okay. So let's just find what the different components of surface diffusion are. So like, if we try to write the PD, we need to let's just write like the different things that will go, the different ingredients that will go into writing of the equation. Okay. U is equal to x of xt. The main curvature, if I'm not mistaken, is equal to the second derivative of that. Yeah, I'm gonna forget this we have. The normal of uxt will be equal to this one. And finally, the Laplace-Bertrami operator will be equal to just apply the definition. X. Again. I don't have enough space, so I might rewrite it. Is this clear, or you want me to rewrite this? Okay. So we take the Laplace transform. So then we just plug into the surface. I will not write the details, but let's just write like the form of the equation. So how will it look when we plug everything in? And when we're looking at this, is kind of a classical way to look at like PDEs. So surface diffusion with a parametrization will be this form. Of the following form. Dt of f is equal to dx to the fourth of f times a function g0 of the derivative of f for the function g1 of like f x to the of f. So all the derivatives and of f. So g0 goes from R to R, g1 goes from R4 to R. And of course, when initial condition f of x0 is equal to 0 of x, this is the initial condition. I'll just write for initial condition, I'll write I. Okay. So what does it mean to prove well-posedness? We are looking for a pair of spaces y et such that if f0 is in y, then there exists a unique, I'll just call it PD star, a unique f in ET, which solves star. Okay, that's what we mean by well-posedness. Okay. It also means that we will not talk about it, that the solution will continue to depend on the initial conditions, but okay, we don't look into that now. So T corresponds to the time interval. So it's an evolving hypersurface, and we want to show well-posedness for some time interval. Sometimes, like the solution will blow up, so T will not necessarily be infinite. And actually, the steps we will use to prove it, we will actually first prove it for a very small t, and then we will extend the t, if we have enough time to do it. So, so let's first see what spaces we look for. And then, no, actually, I'll first give the steps, the different steps. So you guys keep them in mind while we're like looking or presenting the different ideas for how to prove it. And then I will present and then I will give the spaces. So the steps are as follows. One, so prove well-posedness in the same spaces for y pt for the following PD. So we start with the linear PD. So it's dt of f. So these first look the same. F of x0 of 0 of x. Okay. Is equal to the x to the fourth of f, again the same, but here what else we think we change? Of g, okay, so g equal plus h of xt, actually h of x, h of x, h of xt, h of xt, and dx of g, g will be in the space of initial functions. Right, we can do both, but let's just do this one first. Okay. So h of x. So g will be in the space of initial conditions. And yeah, so this is the idea. So you see the linear PDE. So we first prove the existence of a linear PDE, and then what we'll do, we'll use this result to prove well-posed for the nonlinear PDE. Step 2. Okay. So we use Banach contraction theorem. So if you took an LD class, maybe this will remind you of it. Theorem plus step 1 to prove well-posedness of star. And then step 3. So when we apply step 2, like the time interval becomes arbitrarily very small. For small t. The time interval, we have a solution. And step 3 is extend 0t to a maximal interval. Maximal time interval. Interval et max. Oh, sorry, not the interval. 0 to max. And so what does it mean to maximal time interval? It means that beyond that interval, there is no well-posedness in spaces of this form, of the form of et. And we'll define now how the spaces look like. So, and when we do step 3, we will see a motivation for the differential of the spaces. Actually, there's many motivations also for step 2, but we'll not go in enough detail to see the motivating reason in step 2. But in step 3, we will understand a motivation for the definition of those spaces. No. Arbitrary initial condition in y. I wrote x. Define x. Arbitrary initial conditions in y. Like yeah, y disappeared, but I will now define what y is. Okay. So yeah, so we have a parametrization. So the spaces are so et will be h1 of 0. So there's the first derivative. So in time, it's only one derivative. Okay, h1 of 0t, L2 of r. Remember, it's like a function, it's a graph, it's a function of written. h1 of 0t, L2 of r, intersection L2 of r, h4 of r, L2 of 0t. Okay, so these spaces are, so it's 1 times differentiable in time and 4 times differentiable in space, which makes sense because the derivative. So those are very natural spaces, and it makes sense because the derivative is like the operator, because it's a fourth order PDE, as you can see. So one is differentiable. And what does this kind of mean? It means that after we apply the time derivative and after we apply the derivative in space, we want both sides of the equation, or all of the different components in the equation, to be in L2 of 0t L2R. And what's the space of initial conditions? So in this case, it's just going to be H3. So you actually have to be less more than initial conditions. It's kind of a property of parabolic PDE, of this kinds of PDEs generally, that, so this kind of PDE is called dissipative, and generally the solution gets smoother over time. Like you can think of the heat equation as an example. Okay, so step one. Oh, actually, I already wrote the step one there. Okay, so we'll do the step one. We prove well-posedness of this PDE here. So how do we do it? So I'll give like a motivating idea. Okay, so idea. Let's take this PDE here, and I'm just going to define this operator of F. Just define just it's simpler to write. Okay. So the idea is we apply Fourier transform in space on both sides of the PDE. So let Ft from L2 of R, current time, be a Fourier transform. So this is just a Fourier transform. So we applied both sides of the PDE. And I'm also going to move this to this side, like this, you know. F minus A of F is equal to Ft. That makes sense, no? We take A, we subtract both sides by A, and then we apply Fourier transform with respect to time. This is the same as IT minus A equal to Ft of F. Yeah, this is just we apply the basic property of Fourier transform. So this is just the derivative becomes multiplication, and A you can take in and out because A only depends on space. All right, now we will assume for now that this is invertible, so that that T's and IT's in the resolvent of A. We'll just assume it's invertible. So that is equivalent to that is equal to IT to the minus 1, so that's impossible. Possible. Of H. Okay, we're almost done. Then we multiply both sides by IT. So if for those who are familiar with sectorial operators, this will look familiar. And then finally, we just reapply the inverse transform on both sides. So on one side, we get the derivative with respect to time. And on the other side, we get this operator, which is a very commonly used one in PDEs. This operator. So what we want, if you look at the spaces, is for the derivative with respect to time to be in LP. So what we want is for this operator to be in LP. So well-posedness, like there is a unique solution, is equivalent, so just by looking at this relation, to two things. So uniqueness is equivalent to two things. This is uniqueness. Uniqueness is equivalent to two things. To IT minus A being invertible. And let's just say for almost all T in T. And such that F satisfies, and I'm just going to call this equation here double star. Okay. So and then we can show, it can be shown, it's not too much work, that this, well-posedness of star, remember star is the parametrization of RPD, is equivalent to, so you can show that this is equivalent to this. This operator here being a continuous linear operator, so a bounded linear operator between LP of R between LP of R, and itself. So it goes from LP of R to R in time. LP0 to LP of R, and it goes back to itself. So this is an operator that takes a function in this space here and gives you another function in this space here. If this operator is in this space here, is a bounded linear operator between functions in LP of 0t to LP of R, then that's equivalent to well-posedness of the main of star. And this, if that's the case, is called a Fourier multiplier. If so, this is called a Fourier multiplier. And a big part of the theory of, like a lot of the theory of the MPDs, deals with proving that things are Fourier multipliers. It's seeing one operator Fourier multiplier. So we will now use, so we will not show it because it's like difficult. So we'll use a theorem that gives you a condition for operators to be Fourier multipliers. Any questions, by the way? So, theorem. This is due to Deng, who's some German guy, and Hebel. I think it's I didn't write the take. It's from the early 2000s. F to the -1, And this is for general, I mean, this is the theorem is not like this, but this is for general operators like this, not for the A we specifically define. Is a Fourier multiplier if A is elliptic, and its coefficients are sufficiently smooth. So we will not explain what sufficiently smooth means, but it's just like smoothness properties of the coefficients. So we'll not check the smoothness properties of the coefficients, but they'll be satisfied, but we'll check ellipticity of A. So let's check ellipticity of A. That's not very difficult to check. So what's A? A is A of F is equal to root of F times some function G0 of, and G, and those are all the derivative, first, second term, one. So how do we check its ellipticity? We look at the symbol of A. So what's the symbol of A? Symbol of A is just psi to the fourth. Like you just replace the derivative by I psi. Psi to the fourth times G0. And if you actually look at the parametrization, this is more than that. So it's elliptic. Yes. So we check the ellipticity of it. And what does it mean? It means that for the PD in step one, so if you look at your notes for what we call star, there is a unique solution for initial conditions in Y, and the solution is in ET. And in this case, because it's linear, actually the P can be arbitrarily large. Not necessarily infinity, but arbitrarily. Okay. So now we will do step 2 and show there is a unique solution to the nonlinear PD problem. At least give an idea of the proof of how to show this. And kind of the idea of the proof of this thing is we use kind of the ideas from OD theory. So it's you kind of generalize the tools using OD theory to PDs. And in the details, to be able to do that, it's important that we have nice enough spaces. So the spaces we use right now are those, are nice enough for us to be able to do that. If you use the space, for example, you're studying the PD course, the operator goes from H1 to H, for the heat equation, you have a solution in H1 or something like that, is not enough. Oh. Step 2 is to the fixed point argument. So the surface diffusion, so the parametrization, is of the following form. If you remember, I mean, this is equal to a PDE of the following form. So this is what's called a quasi-linear operator plus G1 of F. So A is A of G of F is defined just to be, so it's almost the same as A of F and AG of F, they're almost the same. The only difference then, A of F is for some fixed G, This you can also vary to G. Okay. And then the initial condition is F0x. Okay. So we take this PDE, and kind of the idea, we want to create something that looks the same as the PDE from step 1. But that in certain situations will be the same as this PDE. So we set up the following PDE. The PDE will be dt of f minus a of f0, this is f0, it's the initial condition, of f is equal to g1 of v. I will say in which space v is. A of f0 v plus a of v of v with v in t. Okay. So just let's look at this PDE for a second. If v is equal to f, okay, then those two cancel. Okay, we can, and then the PDE actually looks the same as this PDE. You also notice that this is a linear PDE. For every v, we have a linear PDE. Because this is f0 is fixed, v is fixed, so this is a linear operator. So what we will do is we will say, we'll just. Sorry? No, G is equal to F is nonlinear. Because, yeah, because you're multiplying things that depend on F by F. But if G is frozen, if G is different than F and G is fixed, then it's linear. That's the idea. Because just some function multiplied by like a derivative or like a fourth order derivative or something. So yeah, and the idea here is that you want to say this is like if you freeze v and you freeze f, this is just a function. So we can just define this as a function h of xt. Okay. And if we fix this a function, this PDE will look familiar. It'll be the same as the PDE we saw in step 1 with g just equal to f of 0. That's it. So we actually obtain a linear PDE that we can solve. So oops, does that make sense, or you want me to like write it further? Okay. So, so we have a linear PDE. I'm just going to rewrite it to quickly write the linear PDE just so it's more understandable. It's equal to h. By step 1, there is an exclusion. And I'm just going to write a little bit here to say that, to show that it depends on v. So for every v, by step 1, the above PDE has a unique solution F in E. Okay. So we define the following operator. Define F between ET and ET such that F of E is equal to F. Does it make sense? You give it a V, that this is the V that you plug in, that you have in this PDE, so the V in this little bit here, and what comes out is the unique solution to this PDE. So F of V is equal to the unique solution. To, let's call it three associated with yeah, the unique solution. And then 3 depends on this. So now what are we looking for? What do you think? What we want is to show there is a unique fixed point in there. So we want to show, we claim that phi has a unique fixed point. Fixed point for any initial F0. So given initial F0, phi has a unique fixed point. So for any initial F0, phi of F is equal to F. There's a unique F, so that phi of F is equal to F. This exclamation point can mean unique. There's unique F, so that phi of F is equal to F. That's what we want to show. So in the step 1, we found that you have a linear PDE, we have a solution. Now we apply a fixed point argument. How do we do that? We apply the Banach contraction theorem. So how do we show this? Do we show this? Show this Banach contraction theorem. Let's just orally say what I'm going to recall the theorem. The theorem just says that if I'll just say what is it? Like if two properties are satisfied, if phi satisfies two properties, then there is a unique fixed point. So we need to show that phi of ET is ET. Property 1. Property 2, that phi is the contraction. Phi of E1. So this is Banach contraction theorem. You satisfy these two properties, then do an R alpha. Okay. So if these two properties are satisfied, then there's a unique solution. And that's kind of like, it goes back to like ODE theorem. To prove those, like we're not going to do it, but like to prove those two properties, we use the actual definition of the spaces. So actually, it turns out that defining those spaces tells us that the this operator here, di t minus a, and the tuple with this operator here and the initial condition, and the operator that gives us the initial condition is an isomorphism. And we have an isomorphism between Banach spaces. We have like we have equivalence of norms, and that gives us estimates. And by using those estimates that come from the equivalence of norms, we can prove this thing. And also we need to show that A satisfies certain Lipschitz properties, but that's kind of the idea. And this creates also, again, the classic idea of PDEs. But the difference between when they usually do it and when we do it with our definition of spaces, or like if you do it with like weaker spaces, is that we would not be able to apply step 3 squeezing. So the time. Step 3. Extend to a maximal interval. Small interval of existence. So by using trace theory, whatever that means, or interpolation theory, whatever this means, we can show ET is contained in C0T of Y. So it's continuous between 0T and the space of initial conditions. All right. It's created, and this is called a trace space. When you have something that's non-measured, like a solution that's non-measured 0, and you go to something that's measured 0, and the act of going from something non-measured 0 to something measured 0, you call it's like you're applying operator. The restriction they call is called like a trace operator, because a priori it doesn't necessarily make sense. It's well defined for interval spaces such as L2 and so on. All right. So the idea is this: for any initial f0 and y, we can show just a unique f in this space here, C0T y, which solves the PDE, which solves surface diffusion. Oh. But not this, it's like close brackets. So we can set up a new PDE problem. A new PDE problem with as initial condition, f of xt. Doesn't this make sense? So we have a PDE. We can show using step 1 and step 2 there's a unique solution on this interval. And at this point t, we say, oh, now this is the initial condition. So then we can extend it a little bit more. So initial condition, let's just call it f0, 1 equal to okay. So and then we do this again. So this lets us extend. We can then extend the solution f to a solution f1 in Et prime, where T prime is strictly more than 2. Oh. And we can keep doing this inductively. And because we can keep doing this for arbitrarily a large we can just keep doing this forever until we get like a half open interval. Like then we take the union of all the extensions, and then we can get a half open maximal interval. Sorry? Yeah, so no, because you can actually prove that this space in the solution is in this space here. So actually you know what happens at it's empty. It's a closed interval. You can prove it's a closed interval. Yeah, and then you can prove it's a maximal open interval. So you just keep applying this, and then you take the union of all the times of all the extensions. So So we can inductively repeat the process. And then to obtain a maximal interval. And this one, half of existing uniqueness. What does this mean? This means that in this maximal interval, you cannot have a space of this form where you have existence of uniqueness. So anything that's stronger, anything that's like smooth or whatever, or anything with like actual like Holder spaces or things like that, you will not have an interval of its uniqueness on an interval that's larger than this. And Tmax can also be equal to infinity potentially. And Tmax will depend on initial conditions and will generally be characterized by like singularities. So things that blow up, things like that. And I mean, you can actually have like functionals that characterize this interval. Okay, so we don't have much time, but I will just quickly give an idea. So this is the well-posedness section, and I will just quickly go through linear stability. Okay. So the steady state what does it mean? It thinks that of surface diffusion are constant mean curvature surfaces. So you can prove it if you look at the gradient flow expression of surface diffusion. It's easy to see. What's the steady state like? Because surface diffusion is a PD of this form. So steady state just means it satisfies this PD. So it does these, the velocity is like the time derivative is on this side, so it just means it doesn't evolve over time. So you have a surface that does not evolve over time. It just stays stagnant and solves the PD. So an example, like as an example, there's a straight line. Like you remember the parametrization that we had? I mean, this is not straight, but like, so if it's a straight line, it will solve like the mean curvature is constant. And you can also see the Laplace transform of the mean curvature of something constant, of the mean curvature of something constant is equal to 0. You can actually see that. You just take the derivative of a constant is 0. So this is how it looks. So the question is, if you perturb it by epsilon, so you find the perturbation, like use a different color. You have a perturbation, for example, something like this. Okay, it's not a very nice drawing, but if something that looks a bit different, the question is, do you go back to the steady state? I'm just going to try to make smaller, but maybe a bit better drawings to make more sense. The question is, you perturb it by epsilon, does it go back to how it was before? Or is it something different? So this is the steady state. You begin with this. You perturb it. Maybe we'll look something like this. And there's two options. Option one, it goes back to the steady state. Option 2. Option 2. It becomes something else, something completely. All right. So if this happens, we said it's linearly stable because the perturbations are arbitrarily small, or small enough perturbation. Stable, and this is like unstable. I mean, if it's linearly unstable, it's actually nonlinear unstable, so we can just say unstable. So we kind of want to study the stability of the steady states. And by the way, if you're linearly stable, then you have and in the initial condition is close enough to the steady state, then you have well-posedness for all time. Okay, so I'll just say a couple of words about. So I'll just give the idea. How to find linear stability. So we want to find a criteria for linear stability. So we'll try to just. So the idea of the linear stability is just we look for a criteria. Of linear stability. All right. So the idea is the steady states are going to be they're going to be either local minimums or subtle points to the area function. So you want to kind of, so the idea is, I'll just say idea, steady states are local minimums, are critical points. Points to the area function. So one way of studying that, there's more a calculus versions way, and there's like more PDE type way. So we'll just look at the PDE type way. So what you do is you linearize the PDE, but about steady states. So linearize PDE about steady states. Steady states. By just taking the Taylor expansion of the of both sides of the equation and just taking the first order. So by taking the first order or the Taylor expansion of the Taylor expansion, the first order summoned of the Taylor expansion of both sides of the PDE. It's not the Taylor expansion of the solution, it's the Taylor expansion of the operators. So basically the first variation on both sides of the PDE. And then what you do is, so you take a steady state, you perturb it, you look at the perturbation, you take the Taylor expansion on both sides of the PDE about the steady state, and we obtain, so we still have a gradient. We obtain a gradient flow. And then we can try to test, and then what we do, so we again look if that's a minimizer, and we try to check if the steady state are minimizers of the gradient so tangent ratio of the functional the functional characterized as by the gradient. I'm not going to write how the function looks because I want to leave in the interest of time. But all I'm going to say is that I'm just going to give the space where the function lives, and I'm going to give a criteria based on it. So the functional I goes from h3 to h minus 1. And if I of v is more than 0 for all v in h3, or that v, I guess, Ju is the domain of definition of v, is equal to 0, so we constrain these v's, then the so if I have v for all v in h3, the integral is equal to 0, then I of v, then the surface, and then the steady state, that we study is linearly stable. It is not if and only. We can find a functional, except that we're linear to PDE. We find the functional that corresponds to the linearity, that where the linearity PDE is a gradient flow of that functional, and if that function is more than 0 for all v that satisfies this property, then that's equivalent to the steady state being linearly stable. That's it.